We now turn to section 12, where we switch from binary variables to polynomous, ordered categorical, or ordinal variables. In that connection, we're going to introduce a new model, two-part ordinal model, that is necessary for certain polynomous outcomes. Take an example here, an ordered categorical outcome, the 5-category negative affect item irritability from dataset 3. And if you remember, that the question format was, today I felt irritable, not at all, to extremely. We're going to analyze the first 10 days of this study, of 57 days, and the sample size is 271. If you look at the average correlations as a function of the time distance for this item, you find a fairly high curve, which would indicate a high random intercept variance, a high R-square for the random intercept rather, but a fairly small difference between that lower level and the beginning autocorrelation. So the autocorrelations are expected to be low. Turning to slide 121, we take a look at the univariate analysis of this item. And first we note that the number of subjects with zeros throughout is 52, 19%, this being the most frequent response pattern. And the total number of bivariate cells is 1125. So if you're going to go by this rough rule of thumb of 5%, of having less than 5% significant residuals, that would be that we only accept 56. Now we first consider then the unrestricted multivariate probit model, which has 3 thresholds. There are 10 variables and 4 thresholds for this 5-category variable, and we have 45 correlations. So a total of 85 parameters. So if we look at that unrestricted model, we see that we have a high PPP, and the frequency fit, the residuals, are good both for the response patterns and for the bivariate tables. So a good fit. So that's a useful check to make, which seems to be particularly important when you have polynomous variables. The autoregressive model of order 1 has a fairly low PPP, and we have a misfit for the most frequent response pattern, and too many significant cells in the bivariate table, so a poor fit for that. Go into the random intercept AR1, so adding 1 parameter, PPP improves dramatically, and we have a much better response pattern fit and much better bivariate fit, 32 being less than a 56. So a good fit. If we do this by WSMV, we have sort of a marginal fit here. The response pattern frequency fit is still good, but I call that a marginal fit. But the base version indicates a good fit. Now we can turn to our RI-ARMA 11, so AR1 and MA1, which may be a particularly useful model when we have this many time points, 10 time points. And you see then that you have a good chi-square fit. It can only be fit by WSMV. We don't have base for that yet, at least. And in terms of frequency fit, we have a good outcome, so a good fit for that. And comments here at the bottom say that models 3 and 4 both have sizable random intercept variance. The random intercept R-square for RI-ARMA Y stars is about 0.5. Only 3 of the 9 autoregressive coefficients are significant, however, which agrees with the correlation plot. Turning then to another example of a polynomous outcome. This is from dataset 1, the combined study. So we're looking at this 5-category alcohol risk variable. And we're also going to take a look at the 8-category heavy drinking variable. So here now sample size is bigger, 1375, and we have 8 time points. 5-category alcohol risk is distributed this way, from abstinence to low risk to medium risk to high risk to very high risk. The most frequent pattern is 312, has frequency of 312. Total number of bivariate cells, 700. 5% is 35 of those. Now the unrestricted multivariate probit model then has 8 times 4 thresholds. We have 4 thresholds for 5 category variables. We have 8 variables, and we have 3 thresholds, that is no structure imposed on the means or probabilities over time. 28 correlations, so 60 parameters. The number of significant response pattern residuals, 5 for patterns with observed frequency 312, 46, 12, 6, 6. So here we get the most frequent pattern, 312, which is underestimated as 267. So that's a bad fit. And the number of significant bivariate cells is 273, which is 39% of all the bivariate cells. So the frequency fit is terrible here, and we conclude that a new model is needed. So now we're going to turn to a new model here. I'm going to take a close look again at the bivariate case for ordered variables, where you have, in this case, 5 category variables, so 4 thresholds. And the probit model for the 2 variables in this figure, they have number of parameters equal to, well, the number of thresholds minus 1, number of thresholds minus 1 for the second variable, plus 1 correlation. So thresholds plus 1 polychoric correlation. So that becomes C1 plus C2 minus 1 parameters, for C being the number of categories. So 9 for C equals 5, 9 parameters for the unrestricted probit model. The unrestricted multinomial model for 2 variables has the number of cells, total product, minus 1, because they have to add to 1. So we have 24 then for C equals 5. So this is the model that we test against when we consider Tech 10 bivariate tests. Now, intermediate models are possible here and seem to be needed. This model, Model 1, is not sufficient. Model 2 is unnecessarily parameterized. So let's look for an intermediate model. And here we propose a 2-part ordinal model for 2 variables, and that has C1 plus C2 parameters. And I'm going to explain to you how those parameters come about. So there are 10 for C equals 5. 10 instead of the 9 that we have here. So just 1 more parameter for a pair of variables. And we're going to see that that makes all the difference. So 2-part modeling then, that's something that us in the Mplus group have looked at before in the context of growth modeling, like a model over on the right here. So we consider a variable here. This is the original variable with 5 categories, 0, 1, 2, 3, 4. And we break it up in 2 parts, whether or not you're at 0 or above 0. So that's a binary variable. And the part of the distribution that's above 0. For continuous variables, we call this the continuous positive part. And although in this case it won't be a continuous part, but an ordinal part. So we did that for, and then you have 2 different models, one for the continuous part and one for the binary part here. And 2-part growth modeling was introduced by Olson and Schaefer in 2001 in the Journal of the American Statistical Association. And I've looked at that in the context of growth mixture modeling in an early paper. 2-part regression analysis with an ordinal outcome, that's something we have looked at as well in this book, Regression and Mediation Analysis. If you look at page 292, we propose that as one possible model for an ordinal outcome. Now, the 2-part ordinal multivariate model, probit model, is something I have not applied before. And to get all the details right, you have to use version 8.8 that's forthcoming. And Tech 10 is then something that has been adjusted to be correct for the 2-part feature. So with 2 C category ordinal variables, there are C1 minus 1 plus C2 minus 1 thresholds and 2 correlations. A correlation between the binary part as well as the ordinal parts. So if you add that up, it becomes C1 plus C2. Here's the Mplus input for how you do this single process unrestricted two-part ordinal model using base. So the use variables that you will analyze are binary variables that we call U, and the ordinal variable parts that we call P. And they are all categorical. And then we use data two-part, which functions in the following way. You have a names list here of variables. They are taken from the names list, and we're only going to work with the Z variables, these alcohol risk variables. And we declare some of them as, when we split this up, the variables as binary, they are the U variables, or continuous, which is, they're not continuous in this case, they're ordinal. Cut point is 0, and here transform is none, whereas for continuous variables, the default is to take a log transformation to pull in the right tail, but that's not relevant, would be wrong for the ordinal case. And then we use the base estimator, and here I request at least 10,000 iterations with thinning of 10 using processes 8. And the model then is that we covary all the U's with each other and all the P's with each other. Now, then we also want to correlate the U's with the P's, but not all of them, because we have the issue that the correlation between, say, U1 and P1 is not well defined, given that we don't observe P unless U equals 1. So we have here an approach, so this is a little technical finesse, an approach that keeps U, T, and PT uncorrelated, and it's described in this RSM paper, section 3.5. So we do a regression of those residuals, P1 through P8 on all of the U's, but then we blank out some of those, 8 of those regressions. Now here it's all of the P1 is regressed on all of the U's and down to P8, all of the U's. But here we're looking at P1 pairwise on U1 to P8 pairwise with U8. So we zero out some of them. So what we're going to end up with is correlations among 16 variables, the binary and ordinal parts, where 8 are fixed at 0. That's through this statement up there. The UP correlation not well identified since P is not observing U equals 0. That's what we're talking about. So we have then 16 variable is 2 times T, T being 8 here, number of time points, times 2 times T minus 1 divided by 2. Those are all the correlations among 16 variables, but then we subtract T, which is the one that we've zeroed out. So we get 112 correlations. Now for the threshold, for each variable, there's one threshold for the binary part of C, and for the binary part, and C minus 1 thresholds for the ordinal part. So missed typo here. So we have T threshold for the binary part, and then for the ordinal part, we have 5 categories to begin with, which means we have 4 thresholds to begin with, and then we take away 1 threshold because we're looking at the 4 highest categories, so we have C minus 2. So T plus T times C minus 2 will be 32 here. So total number of parameters is 144. Now, turning then to a specific model instead of the unrestricted model, let's look at the RI-AR2 two-part ordinal model. Well, this left part here is the same as on the previous slide, so now we're looking at the right part. We define the 2 random intercept factors, and then we do the U autocorrelations of order 1 and order 2, and then the P autocorrelation order 1 and of order 2. And we do not have these contemporaneous covariances for the same reason as before. So the two parts are correlated only via the correlation between the two random intercepts. And that's similar, analogous to what we do in two-part growth modeling. If you look at the Mplus user's guide for growth modeling of two processes using two-part, they're only correlated via the random intercepts or random slopes in the growth model. So let's take a look at what we get here for the analysis of the 5-category alcohol risk variable. So at the top we used the regular ordinal probit model. That was not sufficient. And at the bottom we have the two-part. So again then we look at the regular ordinal probit, unrestricted model with 60 parameters. We get a very good PPP, which shows that the correlations are well fitted, as we would expect them to be. But we have badly misfitting frequencies, response patterns in the bivariate tables. This is the most frequent pattern, and it's ill-fitting. And we have way too many cells in the bivariate tables that are poorly fitting. So here's a good example of the case where it's really important to not only show fit to the correlations, but also fit to the data. For AR2, we do equally poorly. We just restrict this model further, fewer parameters. Of course, that's going to fit even worse than 60 parameters. So we turn to the two-part ordinal model, the unrestricted model then, which has 144 parameters that we decided on. And we get a good fit here and a good fit for the frequencies. 29 cells significant, only 4%. It's true, we have far more parameters. We go from 60 to 144. But that's what's needed here to fit this model in the unrestricted case. Now, for the AR2 model then, we get a decent PPP, but I would say a poorly fitting frequencies, particularly here, 15% instead of 5% or less. Going to RIAR2, we get a decent fit in the frequency sense as well, so we can stay with that. In this case, we cannot yet do RI-ARMA. It's not available for the reason that RI-ARMA can't be done by base yet, and RI-ARMA has to be done by WSMV, but WSMV is not suitable for two-part because it does not handle missing data correctly in the correct way that's needed for two-part. Now model 7 then, RIAR2, it's a good model, okay, fit, has sizable variances for the two random intercepts. The two random intercepts for the binary and the ordinal part, where the R-squares range from 0.3 to 0.6 with slightly higher values for the binary part. In contrast, it's interesting to see that the regular ordinal probit model 3, RIAR2 as well, has ignorable random intercept variance, estimate less than the standard error, and ignorable R-squares. I should mention that for the analysis that we've done so far, you have outputs on the website for this Webtalk. Let's also take a look at the 8-category heavy drinking example using two-part modeling. So here we have 8 categories, 0 through 7. Number of heavy drinking days per week. This is again from the first data set. And the most frequent pattern is zeros throughout with frequency 503. And we also count the total number of bivariate cells. On slide 129 then you see the regular ordinal probit analysis and the two-part probit. So once again, unrestricted fits well in terms of the correlations, high PPP, but poorly in terms of the frequency data. Poor fit. particularly for the bivariates. If you go to AR2 and onwards, of course, then you restrict the model further and have poor fit also there. So turning to the two-part ordinal model, you have the unrestricted model, good fit for that, and good fit for the frequencies. Much better than any of those up there. AR2, likewise, a little bit low PPP, and here poor fit in terms of the bivariates, a little bit above 5%, but perhaps more importantly that the most frequent pattern is ill-fitting. So we go to RIAR2, increase the PPP, and we have good frequency fit. And again, RI-RMI is not available for the same reason as we mentioned before. And once again, model 7, the two-part ordinal RIAR2, has sizable variances for the two random intercepts, with R-squares ranging from 0.4 to 0.6, with a little bit higher values for the binary part than the ordinal part. And like for alcohol risk, the regular ordinal probit model has ignorable random intercept variance and ignorable R-squares. Now, turning then on slide 130 to the bivariate analysis of stress and alcohol risk for weeks 8 through 16, so t equals 8 again, we return to this question in the introduction. How do stress and alcohol risk relate to each other? Which influences which? And there has been articles discussing that and finding that stress causes drinking. But here we are in an alcohol treatment population, an alcohol treatment setting, right after the treatment has started. And alcohol treatment, that setting may produce a quite different picture in terms of their relationships. Looking at the average correlations here, we have the stress variable that we looked at before with a high R-square for a random intercept, and the alcohol risk, the binary part of it, also seems to have a high random intercept and a higher initial autoregressive coefficient as well. So here we're going to choose a two-part ordinal RIAR2 model for the 5-category alcohol risk variable and an RIAR2 model for stress. The RI-RMI model for stress fits better, we acknowledge that, but can't be combined with two-part ordinal modeling, again because RI-RMI requires WSMV, which does not handle two-part. It's not obeying missing at random, only missing completely at random. So on slide 132 then, we look at the input for the bivariate analysis, and here we do data two-part only for the Z variables, for the alcohol risk variable. We leave the stress variable alone. So we use the continuous stress variable here and the binary part of the alcohol risk and the ordinal part of the alcohol risk. So, and this part then is the same as we discussed before. And here you have then 3 random intercepts, 1 for stress and 2 for alcohol risk, the binary and the ordinal part. And here then you have the univariate relationships, that is AR1 for Y, AR2 for Y, AR1 for U, AR2 for U, that is the binary part, and AR1 and 2 for the ordinal part. And then the bivariate relationships, Y hat regressed on pairwise on U at a previous time point, and Y hat pairwise regressed on P at an earlier time point. And then you have U regressed on Y and P regressed on Y. And we don't regress Y's and P's on each other. So what do you find? Well, so we have stress being Y and alcohol risk being Z. Number of parameters 121. We get PPP of 0.054, a little bit on the low side, but maybe okay. We have really good frequency fit, however. Number of significant response pattern residuals is only 1 with a low frequency, and the number of significant bivariate residuals is 55, which is also quite acceptable here. So let's look at what we find. What are the cross-lagged effects like? Well, Y, the stress variable, regressed on the binary part of alcohol risk, Z. 4 out of 7 cross-lagged effects are significant with this standardized effect size. Y on the ordinal part, all 7 of the 7 possible are significant with a little bit higher standardized effect size. And no effect of Z on Y for either the binary or the ordinal part. So we conclude that increased alcohol risk has a significant effect on increase of stress, not the other way around. So a layman's interpretation of that is when you fail in the treatment, then you stress yourself. Abstinence or not has less of an effect on stress than the higher degree of alcohol risk. Going higher in the non-abstinence categories, towards higher risk, has more of an effect on stress.